What did you say?
I said rotational kinetic energy.
What's that?
What's rotational kinetic energy? I'll show ya! Come on!
Rotational kinetic energy occurs in non-slip conditions, where objects are able to have rotational motion. The rotational kinetic energy equation is 1/2 IW squared, where I equals the moment of inertia and W equals angular speed. The linear analog of this equation is 1/2 mv squared, where m equals mass and v equals velocity. In a system where both rotational and translational motion are present, the total kinetic energy is seen as translational kinetic energy plus rotational kinetic energy. Since the bike's wheel has rotational motion, it also has rotational kinetic energy. However, since it's also going forward, this means it has translational motion. Thus, it also has translational kinetic energy.
Wow, that was so interesting. I want to know more about physics.
Well, physics is all around us, even at this park. Let's go check out some examples.
Okay. What about this? What does this have to do with physics?
Well, this is actually a really good example of rotational kinematics.
Oh.
You know what that is? Well, I'll show you. This is a good example of rotational motion. As you can see, the object is rotating in a circle around a fixed axis.
Rotational motion occurs when objects travel in a circle around an axis of rotation. Circular moving objects are measured in radians. In a circle, if given the angle measurement, you can convert this to radians by multiplying the angle by pi over 180. Just how in linear moving objects we call distance traveled displacement, in rotating objects we call this angular displacement, or how much an object has rotated. The equation for angular displacement is seen as the change in s, or arc length, over radius. The unit for change in displacement is radians. If the object rotates counterclockwise, it is positive, while if it rotates clockwise, it is negative. The next one is angular speed, or how fast the object is going in a circle. The units for this one is radians per second, and the equation for this is angular speed is equal to change in displacement over time. The linear analog for this is velocity. Next, we have angular acceleration, changing speed of an object going in a circle. Angular acceleration equals the change in angular speed over time, and this is measured in radians per second squared, and the linear analog for this is acceleration. Next, we have the 5 equations for rotational motion, where A is constant. These equations are the analog of the linear kinematic equations, where A is constant as well. If you know 3 of the 5 variables, you can find the other 2 through these equations. As we can see in the example we use, the object spins around an axis, the pole, and we can find the radius and arc length, and from there can determine change in displacement. And by spinning it for a certain amount of time, by using change in displacement and the time, we can find the velocity. Furthermore, if we started the object from rest, we could use the final velocity found and divide it by the time to find acceleration.
Wow, that was so interesting. What else is there here?
Well, actually, this is a really good example of conservation of angular momentum. I'll show you.
This is an example of conservation of angular momentum, where the person bringing their arms in versus out. Now I'll explain more by writing it out for you. Angular momentum is conserved provided there is no external torque acting on the object. The equation for angular momentum is L equals I times W, or angular momentum equals the moment of inertia times the angular speed. In our example, since angular momentum was conserved, we can write the equation as Li equals Lf, or the angular momentum initial equals angular momentum final. Since both sides must equal each other, the variables will be going up or down depending on what is happening. In our example, when her arms were out, she was creating a larger radius for herself, which increases the moment of inertia, because moment of inertia equals mr squared. Since the I went up, velocity must go down. However, when her arms are out, she's creating a smaller radius for herself, which in turn creates a smaller I, and the velocity must go up.
Wow, that conservation of angular motion was super cool. But what was that moment of inertia thing you were talking about?
Well, let's go check another example out about that.
Oh, great.
So how are we supposed to demonstrate the moment of inertia? Well, we can demonstrate it using, a soccer ball I brought and a cylinder, but I didn't bring the cylinder. Good thing I brought my hot chocolate! Perfect!
This is an example of moment of inertia of a sphere versus a cylinder down a hill. We can describe moment of inertia by how difficult or easy it is to make something rotate. The bigger moment of inertia, the harder it is to make the object stop or go. Moment of inertia is the rotational analog of mass. However, it's not just about mass. It's more about the placement of the mass to where you're trying to rotate the object. Some objects that have a set moment of inertia equation are a sphere, cylinder, and hoop. The equation for a sphere is I equals 2/5 mr squared, where m equals mass and r equals radius. The equation for a cylinder is I equals 1/2 mr squared, and the equation for a hoop is I equals mr squared. Since the mass of the hoop is concentrated on the outer edge, it's the furthest from the axis of rotation, making it have the biggest moment of inertia. For objects that don't have a set moment of inertia equation, we call this a point particle, such as a human or any other object, and the equation for this is I equals mr squared. In our example, the sphere rolled down the incline faster than the cylinder. This is because the sphere, or the ball, has a smaller moment of inertia than the cylinder, making it easier to rotate or go.
Wow, this has been such an exhausting day of learning about physics. Let's go inside. Good idea. Whoa. You gotta push here, further away from the pivot point. It's all about torque.
Whoa, thank you.
You're welcome.
Just as forces make things move, torque makes things rotate. Torque is equal to the product of the distance between a pivot point and where the force is applied. Thus, the further from the pivot point, the more torque. The closer to the pivot point, the less torque. As well, torque causes things to angularly accelerate. The equation for torque is seen as T equals Rf sine theta. R being the radius from the pivot point, F being the force applied, and sine theta is the angle to the radial line. For an object that has rotational motion and is in equilibrium, the net torque will equal 0. In our example, Paige is not able to open the gate because she is pushing on the hinges and there is no radius between her force and the pivot point, so no torque can be created. However, Cameron can open the gate because she is applying a force the furthest from the pivot point, creating lots of torque. Since Paige and Cameron are applying a force at 90 degrees, we don't need to worry about the sine theta, since the sine of 90 degrees is 1.